He kōna e purangi tēnei nā te reo irirangi o Aotearoa.
Just over 30 years ago, this happened.
Whoa. That's a beauty. Now get ready to run, guys.
A dramatic eruption on Mount Ruapehu, a plume over 10 kilometres high.
Massive columns of grey and black going up and then just bursting in like a starburst and flinging out rock all around and just expanding and getting bigger and bigger.
Skiers fled the mountain as ash and debris rained down. The eruption triggered lahars, mudflows that spread down 3 of the mountain's valleys.
High and wide, dark cloud billows and swirls and rolls and sweeps down the side of the hill.
Luckily, there were no deaths or serious injuries. And since that time, there have been great advances in monitoring and modelling volcanoes. But we still can't look inside a volcano to see exactly what's going on. Now researchers in Wairakei are trying to do the next best thing: recreate it in the lab. Kia ora, nau mai haramai ki te ao hurahanga. Hello and welcome to Our Changing World. Ko Concannon tēnei. Ruapehu, the North Island's highest peak, sits within the Taupō volcanic zone. Off the east coast of the North Island, at the Hikurangi subduction zone, the Pacific plate is getting pushed below the Australian plate. As a result, the Earth's crust here is stretched and thinned. This means earthquakes and volcanoes.
We have a series of volcanoes that stretches from Ruapehu in the south, and then we have Ngauahoi, and then Tongariro, and we have Taupō, which is under Lake Taupō, just to the south of us. And then we skip forward to the north to Okataina volcano, which is right next to Rotorua, and there's also Rotorua volcano. And then from there we go out to Whakaari, which is in the Bay of Plenty.
This is Dr. Oliver Lamb, a volcano seismologist at Earth Sciences New Zealand. He's originally from Wales, a place not known for its volcanoes. But when 8-year-old Oliver visited a volcano in the United States, he became completely fascinated with them.
Maybe a year or two later, just sitting in school with a careers counsellor, they're asking me, what do you want to do in life? And I said, I don't know, what do you like? Volcanoes. I said, you could do that. I said, okay, I guess I'll do that then. So I think I'm extremely lucky to end up in a position where I'm doing what I dreamt of doing when I was a kid.
Oliver worked on volcanoes in Chile and Iceland before arriving here, at Earth Sciences New Zealand's Wairakei Research Centre, just a few kilometres north of Taupō. The collection of buildings here has about 80 staff, some working on volcanoes, others working on groundwater and geophysics, but there's also a large focus on geothermal, the original reason the lab was set up here.
We're right next to the Wairakei geothermal plant, which is one of the first in the country, one of the first of its type in the world, actually.
Wairakei's first generator is slowly brought into operation. 1.5 megawatts is reached and the first power from Wairakei flows into the national grid. As the generators spin, they pump power coming from 2,000 feet below the Earth's surface, power to cities 100 miles away. History is made today. Wairakei is a power station with a difference.
That clip is from when it opened in 1958, and can I say, I just love those archive news clips. The music is so dramatic. Oliver and I are standing just outside the research labs, which are on a bit of a rise, so we're looking down at State Highway 1 and the power plant, all shiny pipes and escaping steam. The thinning of the Earth's crust in this region creates the bubbling geothermal pools that are attractive to both tourists and power companies.
A lot of geothermal plants in this area, and there's a new one that just opened just over the hill over there of Tohara geothermal plant, and not too far away is Rotorua, which is where they've selected as the trial site for the supercritical geothermal borehole. So it's a really active area for geothermal power generation.
Supercritical is a physics term for extremely hot, pressurised liquids or gases. And we'll get back to supercritical geothermal a bit later on. But let's refocus on Ruapehu. Volcanoes come in several different flavours, defined by their rock type and shape. So Ruapehu is an andesitic stratovolcano. It's roughly a cone shape made up of alternating layers of ash and lava flow. That's the stratovolcano bit. The important thing to know about andesite rock is that it has quite high silica content, which makes it stickier, which means gas finds it tricky to escape, which means Ruapehu has a greater chance of explosive eruptions.
It also has this sort of very active hydrothermal system at the summit with a lake on top of it. And that amount of water present around the vent means it very often has these kind of eruptions called phreatic eruptions, with these gas-driven, sort of fluid-driven eruptions. And that means there's no magma or very little magma involved in the actual eruption itself. It's just the eruption itself of supercritical, super hot gas and water coming out of the system because of the seals breaking.
Even though we can't look inside Ruapehu, we do know a little bit about its anatomy. There's hot magma deep below, and that sometimes moves upwards. This shallower magma then heats the rock and fluid under the crater lake. Think of the hydrothermal system as a series of pipes, acting as escape routes for the gas and hot liquid to seep into the crater lake through vents. One key theory as to why Ruapehu erupts is that as the temperature rises, a mineral seal may form in these vents, behind which pressure builds and builds until...
If you were there to look at this, it's spectacular.
This is Dr. Lucian Saikowski, a hydrothermal geochemist. He's not talking about Ruapehu though. He's talking about an experiment to recreate eruptions in the lab.
But unfortunately, most of those eruptions during those experiments happen overnight. So we came back next morning and it was already done and dusted.
Right, so you've not been in the lab when it's happened?
No.
I know when something good has happened because I'm sitting in my office over there and I can see Lucic and Jeff walking past, like really excited, like kids in a sweet shop, you know, just like, oh, something's happened. Oh, okay, yeah.
We are getting excited.
Come and look at the syringe. An eruption in a syringe.
Yeah, now when you say that, I hear it doesn't sound that exciting, but at the time it is.
Yes, a syringe. The eruptions involve a small volume of liquid being pushed out under high pressure into a syringe, once every 50 or so days. However, once Lucian explained the experiment to me, I understood their excitement. By the way, Jeff is Dr. Jeff Kilgar, a senior volcanologist who's leading this volcano experiment. Lucian, Oliver, and I are in the experimental hydrothermal geochemistry lab. And this volcano recreation, to study the seal formation and breaking, is all taking place inside one particular piece of equipment. It's a series of shiny titanium containers, pumps, pressure vessels, ovens, and tubes, designed to allow them to flow heated, pressurized fluid through rock over a long time to see what happens. The heart of the experiment, where the action happens, is the pressure vessel.
Quite heavy, chunky bit of metal with crushed rock inside. So for this very experiment, we are using Ruapehu andesite. That looks like this.
It looks like quite dark grey sand. Dark grey and silver sand.
Yeah. And we crush rock to increase surface area. So if we had a big chunk of rock, which we could have, everything would take just much longer. But because we are crushing it, there is so much more opportunities for interactions of the fluid with rock. Then we don't have to wait for 10 years. We can wait just for a month.
The fluid they're using is the exact same chemical makeup of Ruapehu's crater lake fluid. It's really acidic, so the titanium is key to prevent corrosion and other chemical reactions.
So we've got this pressure vessel with rock. It's heated up to 200 degrees. And every day the system is releasing 24 milliliters of fluid. And then we can compare chemistry of this, what's after reaction with rock, with what's before. And we can see how it's changing over time.
As well as the daily fluid samples, they're also taking temperature measurements every 5 minutes and collecting data on the pressure every second. Because this is key to knowing when the seal starts forming and then ultimately breaks.
The theory behind this is that once the magma is penetrating towards the surface, it heats up the water that's already within the rocks in the volcano. And once it's heating up, it changes solubility of different minerals that are dissolved in the water.
If you think of dissolving things in water, your first thought might be that warming it up means more of it will dissolve, like sugar in tea. But some things work the other way. Think of limescale forming in a kettle.
Some minerals, once it's getting hot, start to precipitate and then creates a seal. So the magma is still going up, the temperature is going up, the pressure of the steam is going up, but then you seal it with some minerals so it cannot escape. But at some point the pressure is so high that it destroys the seal, and it's even strong enough to be detected on seismometers.
So this is what they're trying to recreate. The heat and pressure that the water and rock under Ruapehu experiences when magma rises upwards, which, the theory goes, leads to mineral precipitation, seal formation, pressurization, and finally, bursting.
And why we're doing it? The main reason is that we hope that there are going to be specific signatures of this in the fluid, that we can see like, oh, the seal is starting to be created, which will help us to say like, oh, it's coming, meaning that probably there are going to be those events happening. Therefore, eventually there are going to be explosion, giving us maybe another week or another 2 weeks of warning before the volcano explosion.
That's the pipe dream for now. Oliver Lamb stresses that there is still a long way off being able to confidently predict whether and when Ruapehu will erupt. But the theory links with evidence from the volcano itself. After the last eruption, in 2007, rocks that had been blasted from the lake were found with some globby yellow gook on them. It was sulfur-rich minerals jamming up the pores of the rock.
We can't be 100% sure where exactly it came from. Like it could have probably come from the top of the lake where there's no seal, or it could have come from deeper. We don't really know, but we see this evidence of the sulfur filling all these pore spaces that fluid could otherwise move through.
Following some control experiments, they've now had 3 eruptions, where Lucian has arrived into the lab to see liquid and tiny bits of rock and ash in the eruption syringe. And they can see the pressure changes too in the data. Lucian's a geochemist, so he's interested to see what kind of reactions have happened between the rock and crater lake fluid. After the pressure builds up and then sharply drops, indicating that the seal has broken, they stop the experiment, take the rock out of the pressure vessel, and view it under a scanning electron microscope to look for leftover bits of seal.
What's beautiful about our system as well is that now we know, because we took the rock out, so we can see that this is the mineralogical change to the rock, but also because we monitor chemistry. If there is a mineral that is being created and it consumes potassium, then you would expect that the sample should have less potassium because it's consumed to create minerals. So now we can see holistically all of those informations and perhaps use it in future as well in the monitoring of volcanoes. So if we know that every time before the seal creation, week earlier, the potassium will drop because it's starting to create the seal, then maybe this is something we will have to monitor closely. But I don't know yet if it's this. That's probably going to be potassium, but let's see.
With his focus on geochemistry, Lucian is also involved in some of the geothermal power company work that the research centre is known for. Precipitating minerals can also coat pipes, and interactions between fluids and gases can lead to corrosive acids forming.
Our clients are mainly New Zealand, but not only, the geothermal industry from around the world, and they would supply us with their geothermal fluid, with their rock, and ask to see like what's going to happen if you're going to reinject CO2, or what's going to happen if we're going to add some acid, or what's going to happen if we're going to just let it go like it is for months. So there are always questions, and they are very site-specific, so we're busy because everyone needs our help.
Right, so that's like a commercial side of what's happening here in Wairakei?
That's correct. Like we do research corrosion for Japanese clients, or we are doing CO2 reinjection to decrease the emissions from geothermal industry. The idea was to just reinject CO2 back to the ground. But the question was, what's going to happen with this CO2? Is it going to precipitate as carbonate minerals? It's changing pH. Is it going to cause dissolution of mineral or maybe precipitation? And to drill a well, it's expensive. So to minimize costs, it's cheaper for the industry to come to us and do the small-scale reinjection than try it in real life and risk failure of a well.
To accommodate all this work, and to look to the future, at the end of last year, they got a new piece of kit.
In the room next door, we've got the newest baby of our laboratory, just delivered in last year in December. And
wow, it's very shiny.
It is.
And it comes in its own cupboard.
Oops,
Yeah.
Yes, that's right. And we worked with French engineering company, Vinci, and we designed it for us. So this is only one in the world. And the difference between this one and the old one is that we can have mix of 2 different fluids at one time, and the temperature can go up to 600 degrees, which is good for future geothermal where we are looking at supercritical conditions.
This new, one-of-a-kind piece of equipment is a geothermal process simulator. And it's quite aesthetically pleasing. It's in a steel-framed clear glass cabinet, a bright red cover on the ovens, and of course, shiny titanium pipes and cylinders throughout. And the hope is that it can help with New Zealand's goal of giving supercritical geothermal energy a red-hot go. This means making use of the heat that's deep below the Earth's surface. But there are a lot of technical challenges.
Because it's so hot and at different pressures than traditional conventional geothermal fluid, it's not really a fluid anymore. So in physics, they call it supercritical condition. So it's something between gas and fluid. So we need to study, does it gonna cause precipitation the same way as a traditional water? Will it travel the same way as water? Will it transfer heat to the well the same way? And if we were able to drill to that high temperature, it means a lot of energy from one well, which means efficiency.
Cracking that efficiency is what the government's hoping for. They've committed up to $60 million from the Regional Infrastructure Fund to support the development of the first well. And as Oliver Lamb said, nearby Rotokawa was announced as the first site for exploration just last month. But back once more to Ruapehu, and to Oliver, whose interest and focus is less on the geochemistry side and more on the geophysics. In particular, volcanic earthquakes. Seismometers on the mountain continuously monitor for any movement of the Earth. But this could be due to rocks rubbing against each other, which is kind of your classic earthquake, or because of hot fluid or gases moving under the volcano, which produces what are known as long-period earthquakes, an umbrella term for a whole bunch of earthquakes that look a bit different on a seismograph to your typical earthquake.
And then another kind of earthquake that we quite often see are these sort of tremor. And this is a really interesting form of volcanic earthquakes. And essentially what that is almost continuous earthquakes. Earthquake activity happening because of fluid motion. It can go for minutes, it can go for hours, sometimes it can go for months. An example of that is Ruapehu in 2022. It had this very intense period of activity where it just had the continuous tremor going for months and really quite intense tremor to the point we thought Ruapehu was going to erupt.
Volcanic tremor levels on Mount Ruapehu have increased over the past week and are now among the highest seen in 9 years.
In 2022, RNZ presenter Susie Ferguson spoke to Dr. Jeff Kilgar on Morning Report about these volcanic tremors.
They're not like a tectonic earthquake where a fault ruptures. It's very, very rapid. Instead, if you think of like a balloon that is filled up and then you let the release go, and it makes that kind of blurby sound.
That is actually seismic data of the volcanic tremor from Ruapehu in 2022, turned into sound by then Victoria University of Wellington master's student Liam Branwell. To bring them into the range of human hearing, Liam compressed them in time. That 5-second clip is equivalent to 30 minutes of true time. Like the air escaping from a balloon, this tremor could be caused by gas or fluid escaping through a partial or weak seal. The tremor and other unusual seismic activity went on for months in 2022. But Ruapehu didn't erupt.
One of the big problems we have in volcanic seismology is that we have these unrest episodes at volcanoes like Ruapehu and Taupō that don't lead to eruptions. But sometimes these signals can actually look identical to what's been seen in the past before an eruption. So that's kind of why I'm really keen about these kind of experiments we're doing in the lab, because it can sort of give us a better idea of how to interpret these earthquakes so that in our monitoring operations we can say, okay, this is what we're thinking is happening now. looking at the sort of chemistry and all the sort of deformation or the lake temperature all together, now we have a better idea of, do we think this is probably more likely to be an eruption?
In the lab, they've just started another experiment. But this one has an extra sensor that's of specific interest to Oliver. It's called a piezoelectric transducer.
And essentially that's a little tiny sort of microphone that's attached to the edge of the titanium cylinder. And what that's doing is listening for tiny, tiny micro cracking. And we're measuring sort of just tiny, tiny waves. And essentially that's the link between this experiment and what we're measuring at the volcano, the seismic activity and the earthquakes. So the theory behind that is, are the micro cracks we see in this experiment, can they relate that to the earthquakes that we're seeing at the volcano, perhaps shortly before an eruption that we see at Ruapehu, like the ones we see in 2006 and 2007?
That was the last time Ruapehu erupted. Relatively minor on the geological scale, with not a lot of activity in the lead-up. But it was still enough to send ballistic material into the air, which smashed one of the huts dotting the side of Ruapehu, badly injuring one of 2 climbers that were sheltering there. It's still early days for Oliver's experiment, and all he's heard so far from this sensor is background. But in a previous experiment, they saw some interesting fluctuations in the pressure as it was rising.
And actually that means that the seal was constantly breaking and then re-healing, and the pressure was still building up as we were going up. That's really interesting because it means that it's not just constant sealing process, it's sealing, breaking, then sealing even harder and breaking and sealing and breaking.
Right, you're showing me a graph where there's a bit of a stutter on the
exactly.
pressure as it's building up, but it's still growing all the time.
Yeah.
And is this what you suspect or predict is happening in the base of volcanoes as well?
Yeah, there are some hints in the seismic activity that we've seen at Ruapehu and other volcanoes that there's sort of a build-up on this sort of time scale before an eruption has happened.
And so from what we know of like the seal formation and then subsequent eruptions in volcanoes, what kind of timescale are you looking at for that?
That's the key question.
Right.
Yeah, so volcanoes, we don't really know what the timescale of seal formation is. That's one of the key questions this project is trying to answer. You know, some people hypothesize it could be months, some people have said it could be hours.
And I guess, sure, you know, an experiment like this will give you some indication and perhaps the seismic signals to look out for, but it's not going to be able to recreate perfectly the imperfections of a seal forming at the bottom of a volcanic
Exactly.
crater.
It's not going to be a perfect recreation of the volcano, but it will still be a significant step forward for us understanding what the volcano is doing at any one time.
In terms of that, I mean, obviously you have the seismic data that's going back quite a while.
Yeah.
Do you also have the temperature data and the chemistry data that after you finish running these experiments and you develop this kind of neat hypothesis about what's going on, will you be able to go back and look at the historic data and see whether it lines up?
Yeah, absolutely. I think that's one of the key things to do with these projects like this, is to go back and look at the data again, you know, with a fresh set of eyes, with a new understanding. And that's something we actively try to do in the volcano monitoring operations. We developed these models called conceptual models of our volcanoes. And essentially what these models are trying to do are bring together everything we know about the volcano, what all these research groups have been doing. So say we see change in temperature, change in chemistry and seismic activity, then we can look in the model and say we think this is what's happening in that particular system at that time.
And right now we've got seismic data. There's cameras pointing at it.
There are cameras pointing at it from the base, but not at the lake. We have microphones to listen for just any eruptions. We have GNSS, basically very, very accurate GPS sensors all around the volcano. We have a multi-gas system up there, so that's measuring gases that are coming from the top of the lake. We have lake temperature. We have lake level as well, so we're looking at the height of the water level. In some eruptions in the past, they've seen a sudden increase in the lake because you have all these fluids coming in from beneath. We have what are called DORAS systems, so these are another gas measuring system, but they're not just looking at the gases right by the lake, they're measuring the gases in the plume. We're also taking regular sort of sampling of the lakes. We try to do that on a monthly basis. And
sorry, the other things that you mentioned, that's kind of live continuous?
Yeah, that's live continuous. And then also, obviously, we fly up there and take photos of the lake ourselves, just to look at the colour of the lake, see if there's any big sulphur slicks or anything like that, just to see what the status is of the lake. What else do we have? I think that covers all of it, actually.
It's quite a lot of monitoring. every little movement or change is being detected. But of course, the holy grail is to actually interpret all these signs and signals, to be able to accurately predict with enough warning what the volcano is going to do. Lucien, Oliver, and Dr. Jeff Kilgar are hopeful that these experiments will help with that. In the meantime, experiment number 6 is 5 days in, with the full complement of Ruapehu antacite rock, crater lake fluid, and volcanic gases. So, as much as possible, you've recreated what's happening under the base of Ruapehu.
That's right.
And now you're just going to wait for it to erupt.
Yeah, maybe another 40 days.
Another 40 days. In the meantime, it's kind of very quiet.
Yeah, quite relaxing, isn't it?
Thanks to Dr. Oliver Lamb and Dr. Lucien Saikowski of Earth Sciences New Zealand's Wairakei Research Centre. Thanks also to Liam Branwell for the sonified seismic data of the 2022 tremor. The 1958 Wairakei Power Station clip was from Archives New Zealand. This episode was produced by me, Claire Concannon, and sound engineering was by Phil Bench. Production help was from Kate Newton. In case you're not aware, we also have a monthly Our Changing World newsletter where we share all things science. You can find a link to subscribe to that in any of the episode details on the RNZ podcast page or at the bottom of any of the web articles at rnz.co.nz/OCW. Tēnā koe I whakarongo mai. Thanks so much for listening. I'm Claire Concannon. Kia pai, te wiki.